Hello and welcome to CCNA Subnetting Video 8. This is the last of 8 subnetting videos that are included as part of the ICND-1 and ICND-2 official exam certification guides from Cisco Press. This video shows a process of how to find all subnets of a particular network when more than 8 subnet bits exist. In this particular case, we'll examine Class A Network 10 using mask 255.255.192.0. This video focuses on a particular process to find a few things about a network number. In particular, this process shows how to find all the subnet numbers of a single classful network, as well as identifying the two subnets that are special, the zero subnet and the broadcast subnet. A broader goal for this video is to be part of a package that helps you learn how to answer CCNA subnetting questions, in particular to teach you how to answer those questions quickly and with confidence. The Cisco Press CCNA exam certification guides, as well as some other Cisco Press resources, refer to a one-page summary of any single subnetting process as a reference page. The books explain 3 different variations of processes that can be used to find all subnets of a classful network. For example, reference page 7a is a process that shows how to find all subnets of a network assuming less than 8 subnet bits. RP7b assumes more than 8 subnet bits. There's even a third process described in the books that we didn't bother to name that assumes exactly 8 subnet bits. This video shows an example of how to use process RP7b. However, because process RP7b uses the concepts in process RP7a, this video assumes that you've already watched the video that shows the RP7a process and that you understand that process. This video is designed to show you an example of the RP7b process. However, for easier reference, the generic version of the process is listed here in the video. If you intend to refer back to this part of the video, just make a quick note of the time of the video right now. Also note that the generic RP7b process uses process RP7a, but changes step 6, the last step of RP7a. Also, because process RP7b relies on the RP7a process so much, we've included an image of the generic version of that process here as well for your reference. Now on to this video's example. We'll be examining IP network 10 with mask 255.255.192.0. In this case, there are 8 network bits, 10 subnet bits, and 14 host bits. Now process RP7b says use process 7a until you add something that totals up to 256. So following process RP7a, the first 4 steps, here at step 1 we write down the subnet mask in the top row of a table. Then we put a box around the interesting octet, which is the 3rd octet in this case. It's interesting because the mask's value in that octet is not a 0 and it's not a 255. Then at step 3 we calculate the magic number, which as usual is 256 minus the mask's value in that interesting octet, in this case 64. Then finally at step 4 we write down the classful network number, which is always the same number as the 0 subnet. Next we'll continue on with process RP7a to find the next several subnets. Process RP7a says to keep repeating step 5, finding each new subnet. So in this case at step 5 we'll copy the previous subnet's value for the 3 boring octets, the ones outside the rectangle. And then to find the interesting octet's value at step 5b, we take the magic number of 64, add it to the previous subnet's value in that interesting octet, or 0 in this case. So the next subnet number is 10.0.64.0. For the next pass through process RP7a's step 5, at step 5a we copy the 3 boring octets, then we add the magic number of 64 to the previous subnet number's value of 64, so the next subnet ends in 128.0. Following along to the next pass in step 5, we copy the 3 boring octets, add the magic number of 64 to the previous subnet's value of 128, so the next subnet number ends in 192.0. As you can see, each successive subnet has a value that's 64 larger in the 3rd octet. Taking yet another pass through this process, at step 5a we copy the 3 boring octets down to the next line, then we add the magic number at step 5b to the previous subnet number's value of 192, giving us a total of 256. Of course, 256 is not a valid value in an IP address or subnet number, so that's our reminder to do something different at this point in the process. So, whenever you get to a sum that's 256, according to process RP7B, step 6A, it says if the sum is 256, instead write down a 0. So, we'll simply write down a 0 there in that third octet. Then step 6B says add 1 to the octet, just one octet over to the left. So here that octet was formerly 0, so now we add 1 to it. So the octet to the left, the second octet, will have a value of 1. So the next subnet number will be 10.1.0.0. At this point, all you do is go back to what you were doing before, simply adding the magic number to one subnet number's interesting octet to get the next subnet number. So as you see here, we just copy down the three boring octets, add magic number of 64 to the previous interesting octet value of 0, giving us a next subnet number of 10.1.64.0. Now you just keep repeating this same process of adding the magic number in the interesting octet to find the next subnet number. As you see here, we copy the three boring octets, add 64, the magic number, to the previous subnet number's value of 64, so the next subnet number ends in 128.0. Repeating again, copy down the boring octets, add the magic number of 64 to 128, so the next subnet number ends in 192.0. Repeating it again, copying down the three boring octets, adding the magic number of 64 to the previous interesting octet's value of 192, we get to a value of 256, which is our reminder to say, alright, we're going to do something a little different now. So, what do we do that's different? Well, we use the details that's shown in the generic RP7B process, step 6. That is to say, when you would have written down a 256, instead you write down a 0 in that octet, and then in the octet, one octet to the left, the second octet in this case, you add 1. So in the second octet we add 1 and 1, giving us 2, making this next subnet 10.2.0.0. Now, if you remember that there are 10 subnet bits in this case, giving us 2 to the 10th, or 1,024 possible subnets, obviously we don't want to go through the math for every last subnet. So let's take a look at the pattern that you should see developing from what you've seen in the video so far. There are 4 subnets whose first 2 octets are 10.0, with the third octets being 0, 64, 128, and 192, as you see here. Then there are 4 subnets that begin with 10.1 with those same 4 values in the third octet. Then another set of 4 subnets that begin with 10.2 with those same 4 values in the third octet. Another set of 4 that begin 10.3. Another set that begin 10.4, and so on. So that's the pattern you should see here. Now, if you continue that pattern, you could list all the subnets if you were willing to write them all down, but for brevity's sake, we'll pick the story up at the 10.254 subnets that you see here, and then there's another 4 subnets that begin with 10.255. Now, I know that's the final answer, with that last subnet, 10.255.192.0, being the broadcast subnet. However, for the sake of understanding the process, it's important to see how the process tells you when to stop. So that's what we'll take a look at next. So, to follow the process through to see when to stop, let's just imagine you're writing down these last few successive subnets, the 10.254 subnets, 10.255, 64, 0, 10.255, 128, 0, 10.255, 192, 0, and finally you're adding 64 to 192, and you've written down a 256 in this third octet again for the next subnet. Well, of course you know that when you write down a 256, that triggers the different part of the process as defined by process RP7B. But in this case, it's going to tell us to stop. So we wanted to write down a 256 in the third octet, so instead we write down the 0 and add 1 to the octet to the left. However, in this case, because the octet to the left was 255 already, when we add 1, we'll have a total of 256. Well, the RP7B process says when you want to write down a 256, don't. Instead, write down a 0. So we put a 0 in the second octet, and then add 1 to the octet, one octet to the left. So in this case, following that same logic, we'll try to add 1 to the first octet. Well, of course, the first octet's value is 10. We add 1 to it, and we get 11. So the next subnet number would presumably be 11.0.0.0. However, as stated in the RP7B generic process, whenever you follow this process and the addition causes the network portion of the subnet to change, in this case the first octet being the Class A network part of the number, then that says, oh, you've gone too far. So whenever you do this addition that causes the network part of the address to change, put a big red X through it saying that one's not valid. Then the subnet one above that, in this case 10.255.192.0, is the broadcast subnet. This concludes Subnetting Video 8. At this point, you should practice this process until you can find all subnets of a network with ease. Of course, you can always refer to Appendix D in the ICND 1 or ICND 2 exam certification guide for a few additional practice problems.